Yeah, so I hope now it can be seen. So this is the thing is that though the slide says that our galaxy interstellar medium, but I will start with the interstellar medium first, and our galaxy's interstellar medium first, and then go to our then talk about our galaxy the afterwards. Afterwards meaning near the later part of the talk. So the thing is, for many of you, the many of the participants rather, the interstellar medium is something which, except few nebulas, may not be apparent to you, because typically the interstellar medium is the basically the matter between stars in galaxy and galaxies. Now it remains mostly invisible while observing the sky. So the issue is, because this is gaseous parts, it does emit, but the emission is pretty faint. So the thing is, most often is pretty faint rather. So the issue is, why study the interstellar medium? The first thing is, stars are formed from interstellar hydrogen. So you can see obviously that we can't neglect it. Secondly, more or rather less obvious things are things like stellar outflows. For example, that is, we may think of stars as some kind of a blob in the sky, which is large in size, more like sun. But as you know, sun has solar wind. Similarly, most of the stars have the similarly stellar wind. And this stellar outflows basically makes interstellar medium richer with metals. And number three, the reason for studying is that the stellar end of life products gets dispersed and forms part of ISM. That means, for example, you know that this famous example that we are also formed by supernova explosions. We meaning part of the material like iron, above the things which metals, or rather the um, basically the which lies above in the I forget the name now. That is basically the table of elements, basically that which lies above iron, are more typically formed by supernova explosion. So the thing is that the stellar end of life products gets dispersed and forms part of interstellar medium. Now, how 1, 2, and 3 causes galaxy evolution and feedback to star formation processes. So these three processes are not in general occurring irrespective of each other, they are linked somehow. So one does try to find out this link by studying the interstellar medium. So the thing is that the ISM in general is classified into gaseous medium, but it is not just only gas. There are things like dust, high energy particles, which we also call as cosmic rays, and it has also got magnetic fields. So each of these will come one by one. So first look at how the interstellar medium was discovered. It was discovered more than 200 years back by someone called William Herschel. His name you would have heard in the other aspects, who described holes in the sky where there are apparent deficit of stars. So in 1904, Hartmann found absorption lines towards binary stars. So these are absorption lines were from singly ionized calcium, later on known. So these are basically probably the start, or rather one can say as definitive indication of interstellar medium, because some of these lines moved with stellar motion, that is Doppler shift, but some remain static, indicating absorption of material between stars, so which basically serves as the proof. So the generic importance and proof came from work by Trampler in 1930. So almost like 100 years back, the start of the field of interstellar medium has happened, as you can see. So what Trampler did was to line up the main sequence stars of open clusters to find their relative distance. As you know that the angular size is basically the d by r square. This is the angular size which has been used, and this was plotted against f. F is basically the total light emitted by them divided by 4 pi r square. And both of these should essentially form a straight line, but more distant open clusters basically appear to have systematically lower total luminosity than the square of their angular size. So you are basically plotting, what you are plotting here is basically that the total luminosity you are plotting against their angular square of their angular size, they should form a straight line, but they did not. That more distant open clusters appear to have systematically lower total luminosity. So what does it indicate? That something is taking away their light in between as they go further and further. So there were three explanations, of course, or rather four. One was that the faraway clusters are bigger than predicted by F, then it will make it lower. The second thing is observational selection. The third is faraway clusters are fainter. And fourth is faraway clusters are dimmer due to absorption by intervening material. So it is the fourth one, which is basically the faraway clusters are dimmer due to absorption by intervening material, which became established afterwards. Because observational selection again, the was not found to be significant, and faraway cluster, why should it be? Because the thing is, if the faraway clusters, the main argument goes against 1 and 3 is that if we have to say that faraway clusters are bigger, then we have a special location in the galaxy, because we are measuring distance from us. Now we are not, and remember that we are almost 10 kiloparsec away from the galactic center, which is halfway between edge of our galaxy and the galactic center. So we are halfway in between. So in this halfway in between, there is basically not a special position, as you can see. And why should we have a special position? So then, compared to us, the clusters becoming bigger is very, very unlikely. The same thing applies to number 3, that the faraway clusters are fainter. But again, both of these were unlikely. And number 2, the observational selection again could be ruled out following how they were being selected, because the selection, observational selection, typically affects when you are limited by signal to noise ratio. Here these were not, because these were pretty bright clusters and so on. So the chance of that kind of observational bias were low, meaning essentially unlikely. So this is the way the discovery of interstellar medium took place. Now let's go to each of the components. So first we look at what is the dust. As you know that the dust is responsible already for extinction, but not just that, they could also cause a reddening of objects by scattering of light. They also, which may not be known to many of you, is that they could also do polarization of starlight. And the number 4 is basically the reflection nebula. So all these 4 things, one is extinction, which we see indirectly. Then the reddening of objects are seen more or less directly. Polarization of starlight again in optical has been seen directly. The reflection nebula anyway can be figured out through binocular and or through small telescope even. So the scattering of starlight, as you know, goes nu to the power 4. This is called the Rayleigh scattering. So this causes least scattering in the red part of visible spectrum, and typically the dust size is of the order of the wavelength of light here, optical light. So they cause significant scattering, and typically if it is due to scattering, that is basically reflection nebula, it will basically be looking bluer, because this blue lights has been scattered by the dust which is falling on the nebula, and we are seeing them. Now, what are these dust particles which are composed of? The dust particles are typically silicates, but could be made of or have complex molecules. And the reason why they have polarization is because they have something called the major axis and minor axis. You can think of it that they are like elliptical objects, not like a spherical, they're not like a sphere. They are most often as elliptical or ellipsoid of evolution. That is, in 3D, they look like in a ellipsoid. So then they have a major axis, and obviously along the major axis, the absorption is more. Now the thing is, because they have dipole moment, they essentially tend to orient perpendicular to local magnetic field. And we know that our galaxy as such has magnetic field, the large scale magnetic field, which have typical size scale, or they are organized in something like a kiloparsec scale. So kiloparsec forms a large angular size in our the meaning when we look at. So obviously in different regions of the sky, you would see that the dust particles which are aligned perpendicular to magnetic field and magnetic field lines, that is the regular field, are typically have size scale of the order of kiloparsec. It would call essentially the dust particles to line up perpendicular to the magnetic field often, and this would cause more absorption to the vertical component of the electric field, or whatever you call it. So that way, because the electric field and magnetic field both are basically perpendicular to the line of sight, they are you can think of the electric component parallel or not parallel, sorry, the perpendicular to the magnetic along a line of sight, which are line up in one direction, will cause more absorption. So that is the way the polarization of starlight takes place. Now the thing is that the dust gets heated. How they are heated and what happens, let's see. So the dust gets heated by absorption of starlight, and the typical equilibrium temperature they reach could be of the order of about 30 to 50 Kelvin. And they basically reradiate this whatever the light they are absorbing through the various infrared channel. That means when the that is a typical black body which is the getting heated up by the interstellar light or the starlights, they will re-radiate, and depending on the black body spectrum, typically they are cold, as you can see, like 50 Kelvin or so. The temperature is much lower than what we see on Earth, which is about 300 Kelvin. And as you know that here it will be given by point the 29 by T, which is the lambda m, the lambda max, and that will that will be basically lying in the infrared. And so, as we know, one of the main component of our IR radiation is dust. And what we typically assume, and quite often expected also, that the number density of dust particles goes proportional to the gas density, and hence the dust emission can be used as tracers for certain other properties of the interstellar medium. So for example, if you cannot by the traditional method find out distance towards two different objects, say two different H2 regions, and but you are seeing them in emission, and one of them appears more redder, or then you know that the one which is more redder is likely to be further away. Now, the amount of dust absorption in particular direction provides rough distance estimate for a luminous object. So, that people have characterized, there are various ways to characterize it. You would take a difference between V minus R, so or V minus B. So, these all indicates how much absorption is present, and so that kind of thing people have been doing. Now, let's look at the second part of the interstellar medium, which is the optical nebula. So these optical nebula have different categories. One is dark nebula. Then you can have categories like reflection nebula, which I said already, that bluer than direct light. The number 3 is H2 region, which is photoionized hydrogen gas. Number 4 is the planetary nebula, and number 5 is the supernova remnants. Now, dark nebula is nothing but obscuration by background, meaning what we see as observed by obscuration of background stars. So in certain directions, there are lack of the background stars being seen, and that is typically being thought of due to the dark clouds, or rather more absorption in that direction in some particular distance from us, causing absorption of the starlights. The reflection nebula is of course observed by scattered light from embedded stars. There are also cases like the H2 region. How they form is because there is a hot star which is typically called as O or B type, and they photoionizes surrounding gas by its high UV radiation, forming H2 regions. And the spectrum is dominated by emission lines, and they also have, by the way, radio continuum emission. One example is like the Orion Nebula. So this is typically what we known as, earlier we talked about the dust absorption. So how the dust absorption looks like. So this is the spectrum. This is plotted as 1 by lambda rather, or lambda to the minus 1 in micron. And A lambda, that is the absorption as a function of lambda divided by NH, that is the effectively the normalized by the atomic hydrogen density towards that NH. So if you do that, what you see is typically that there are two lines which are apparent. One is very close to 0, which has been blown up. On the top left, you can see there are two such emission lines which are seen. One is silicate. This is an emission which is being seen because we are talking of the overall emission from them right now, though they are characteristic of dust absorption. Also in the same band, the absorption will also take place. So this is basically, one is the silicate, which is coming at 10 micron. Then the C and H, CH, 3.4 micron. These are the two features at the bottom left, close to zero, which you see. Then the bump around 2175 angstrom is thought to believed to be due to aromatic hydrocarbon. So that is a big bump. So these are the two main features. But in general, otherwise, it roughly forms a power law, what you can expect, except those few places where specific materials dominate. And if you now plot the dust emission in infrared, this is what it looks like. This is the overall, this is not 1 by lambda, but this is rather in lambda in micron. And the other side is the y-axis is basically nu I nu. So that means it has been multiplied by the frequency divided by the normalized hydrogen density. So if you do that, what you can see that at the left side of the plot, that is Kobe and the Firas, so their plots how it looks like the observed emission from interstellar dust. It starts from around 1000 the micrometer, pretty strong. Then it the further increases at about 100 micron, which is the main emission from dust. Then further the how are the other things which is contributing. So it contributes all the way from about 3 micron the up to about almost 1000 micron. These are the areas where the dust emission predominates from the interstellar matter. Okay. And these are the log plots. Next, what I was constant the talking about, we had started about was optical nebula. So let's go back from dust again back to optical nebula. So if you want to just go back, the optical nebula, we had talked about the hot stars which are responsible for forming photoionizing. So a hot star ionizes roughly a spherical region which is called the Stromgen sphere around it. The size is determined by equating the number of ionizing photons from the central star to total number of recombination occurring per unit time, and the temperature of the region, the ionized region, is typically found to be around 5000 to 10,000 Kelvin. So the size is determined by equating, as I said, is important to remember that the size is not randomly determined, but it is basically again the physics which is controlling it, that you are equating the number of ionizing photons at the boundary from the central star to total number of recombinations occurring per unit time. So that is the condition for the balance, energy balance rather. So then the thing is, the H2 regions also, remember, emit something called radio recombination lines, which most of you may not have heard of, because typically we are talking of the main important line which comes in radio, which is the H1 atomic hydrogen. But this is a radio recombination line, certainly not that strong, or the from the interstellar material or the H2 regions. But this is something that is called high the Bohr transition. That means like n is equal to 252 Bohr orbital to n is equal to 251. Suppose the electron comes back to that from very high quantum number to a lower one, the energy difference is so small h nu that they form that they are typically the form or seen in the radio band, which is like say 252 to 251, I believe, comes around 1.4 gigahertz, which is near H1 frequency. But there are many such transitions, and those who studies it, this is somewhat, it's a slightly difficult experiment because you have to have good calibrated instrument to detect them, because the lines are pretty weak quite often. But one can detect it. There are many such lines. So within something like 1 gigahertz to let's say to 1.4 gigahertz, you may have several tens of lines into in that region. So the planet, next we go to, we have talked about dark nebula, we have talked about the H2 region, reflection nebula. Next we go to planetary nebula. So the planetary nebula forms when a white dwarf star shines light on the dense circumstellar material. Circumstellar material means what? That the material which was basically present in the star, around the star, due to stellar the wind. So they had formed. So this planetary nebula is forming basically because you know that before forming a planetary nebula or white dwarf, the star goes through the red giant phase. In the red giant phase, the star basically throws away a lot of material from gets out in the interstellar medium. So that basically so that basically comes in the this band, that is basically that comes in the interstellar medium. So those things gets illuminated so around the star by the central the white dwarf, and that basically makes that there is a compact object at the center, and there is the emission from around the object. So this is the example which I would say as the Orion Nebula, or the one example of the H2 region. The central star is close to the center, shown in white, that is the left side. Not left side, but within the bow. Many of you would know this, but this is a famous example of the H2 region. And this is rather taken from a backyard the telescope, or that is the way. This, if you look at a Hubble image, it will be even more detailed. So next we go to supernova remnants. So these supernova remnants, these are the remnants of supernova explosions. So they are basically the stars of mass typically of the order of 10 solar mass at the end of their life blow up in supernova explosions, releasing about 10 to the 51 hours of energy. The supernova explosion typically initially drives a shock to the surrounding matter ejected by the star in its life, and they could expand at the beginning with a speed almost like 10,000 kilometers per second. During expansion, that is supersonic, it sweeps up matter, forming a shell. So what you can see is that the stars of mass, typically 10 solar mass, which are basically type 2 explosion, they basically at their end, they throw up life, meaning they end up in supernova explosion, but that is not the only mechanism. There is also type 1 supernova explosion, which is different. You can have the central object like a white dwarf, which is remaining, and there is something, a companion. So that companion may be a red giant. If such thing happens, then the red giant, the phase, basically part of it can be eaten up through accretion to the white dwarf. And when the white dwarf mass exceeds basically the 1.4 solar mass, so that the type 1 explosion, on the other hand, when it happens, it basically completely destroys the whole system. It will again give rise to of the order of 10 to 51 hours of energy, because it has exceeded the Chandrasekhar limit. So it will basically not survive, and so this can blow up. So that is called type 1 explosion and type 1 supernova explosion, and this is more used as a standard candle in finding distance far away the galaxies. So this is the Tycho, meaning one example of a supernova remnant. This is Tycho supernova remnant. I believe this was about 1051 AD or so when the explosion took place. So you can see this is a Chandra X-ray telescope. So X-ray detects basically hot gas. You can also have emission in radio, but the radio typically does not look like this often. The meaning there will be more bright, meaning you would typically see age brightening kind of thing. So that happens because the diffusive shock acceleration, which basically generates synchrotron emission or the high energy electrons to velocity close to the velocity of light, that happens near the periphery or where the shock is really for older supernova remnants. But again, there are different types of supernova remnants. For example, if there is a pulsar which is emitting its own material, so then that can form like this. That will look like this in radio. That is field center. But normally they are more look like a ring in radio. So the main thing is that after the explosion, the matter ejected becomes less compared to the swept up interstellar medium, it starts to slow down. Free expansion, which initially it was, because the matter ejected becomes, they basically collide with the interstellar material and they essentially the pile up the near the shock front. So once this piling up of material, which is intrinsic, becomes less compared to the extrinsic material, which it is also accelerating by the shock, it will basically back react on the supernova the expansion, and that will slow down. That's why it goes to adiabatic expansion. The shock around the expansion front causes diffusive shock acceleration to the electrons, causing them to reach velocity close to velocity of light. They emit synchrotron radiation, typically visible in radio. So Crab, about 1,000-year-old, and Casa, the Cassiopeia, a 400-year-old, are some of the well-studied supernova remnants. Next, we go to, so we talked about some basic visible things from the interstellar medium as various nebulas, which we call as optical nebulas. Then we went to supernova remnants. Now let's look at slightly in a different way, which is slightly more meaning involving a bit more physics, which is basically the multi-component ISM. ISM have multiple components broadly with one ionized and two neutral components, and each having multiple subcomponents. For example, the ionized gas can have hot and warm part. The hot is typically thought to be meaning because they have been seen in through X-rays. So they are typically could be hot, as hot as 10 to the power 6 to 10 to the power 7 Kelvin. And the one part is basically, which I talked that day, the previous day I mentioned a little bit about it, which could be like the 6,000, 5,000 to 10,000 Kelvin. So that is basically the ionized gas. The one component was known for long, which forms the H2 region. The hot part was discovered much later. So it is basically the discovery of diffuse X-rays from interstellar material that indicates component temperature of the order of 10 to the power 6 K, which is due to supernova driving hot gas, and they have low density. Now, having talked of the ionized part, let's talk of the molecular, rather the neutral components. So the neutral component consists of molecular clouds and atomic hydrogen. So 21 centimeter emission, as I said that day, was discovered, predicted after the Second World War, and they were picked up after a few years by 3 groups. And roughly about half of all H1 is in warm neutral medium with temperature of 4,000 Kelvin, low volume density, and fields of large part of interstellar medium. Scale height 200 parsec for Milky Way. The cold neutral medium CNM is distributed in relatively dense clouds. Their temperature is like 100 Kelvin. In simple models, all these 4 components exist in stable equilibrium. That means 4 means what? That the ionized part has hot and warm part, and the neutral has basically, you have the molecular component, or rather the cold neutral medium and the warm neutral medium. So in simple models, these 4 components basically exist in stable equilibrium. NKT for each components are about the same. The equilibrium temperature for each of the components are set by near equilibrium of heating and cooling rate also. Okay. So how the cooling occurs? The cooling occurs by atomic processes, for example, by collisional excitation of the fine structure transitions of heavy atoms or ions. And this line, for example, one of the major coolant is 157.7 micron line of carbon 2, that is the ionized carbon. Heating typically occurs by starlight most often. Then also it could be because of energetic ionizing particles, cosmic rays, and C, shocks and waves, through shocks and waves. So the equilibrium temperature are different for different components. Supernova and turbulence can drive shocks. For high Mach number M or a high Mach number shocks, this can be shown that T2 by T1 is equal to 5 by 16 m square, where subscript 1 is for ambient gas and 2 is for gas passing through shock. So if you have a Mach number of 10, you can see that the second temperature could be almost like the 30 times higher. So that kind of thing would happen if it passes through a large Mach number. And we talk about so the supernova and turbulence. So the supernova remnants, as you saw, the meaning as is known, not apparent in Tycho, but like crab, if you look at, it will be very apparent that they can form filamentary structures. And also remember that multiple supernova remnants can join, because if suppose each supernova remnants expands to almost like say 100 parsec, the beyond which of course will be very difficult to detect them, but like 100 parsec size, if there is another supernova explosion which has also taken place in the past, another 100 parsec away, there could be basically two supernova remnants placed apart by 100 parsec, and when each of their radius would reach about 50 parsec, let's say, they essentially can start joining. And many such supernova remnants can join to form chimneys driving galactic outflows. These chimneys are typically perpendicular to galactic plane, and they basically can drive galactic outflows. That means through that chimney, the interstellar medium can flow out of the galaxy. These are known, very well known now. Next, we come to magnetic fields. So the origin of magnetic fields in galaxies is not clear. Could be generated from the primordial field, which is typically a hypothesis, of course, which got amplified due to differential rotation of galaxies forming dynamos. This is one of the significant meaning, one of the interesting models. Most people think this could be the way. But anyway, so the present day magnetic field in galaxies have strength of the order of 10 micro-gauss or so, and they are measured typically by using things like, for example, line of sight measurements can be done either by Faraday rotation or Zeeman splitting. Zeeman splitting is certainly more meaning a direct proof of magnetic field, but they are on the other hand biased towards locally strong magnetic field, meaning in some part along your line of sight there can be strong magnetic field which cause that Zeeman splitting of the spectral line. It could be for H1 or so. So this splitting, on the other hand, you don't know where it lies along your line of sight. That's a major problem in astronomy. But on the other hand, Faraday rotation is the average effects, which we see, and you would have heard of Faraday rotation before, I guess. So, and the Faraday rotation is another thing, which is basically, for example, if your magnetic field along your line of sight is B parallel, and Ne is the electron density, then you will basically see it as NeB along the integrated line of sight. So, integral of NeB dl. dl is the component along your line of sight, small distance, which you integrate over it. So, it is NeB dl, path integral along the line of sight. And remember that these two, which I mentioned, used often, particularly the Faraday rotation in radio, and this gives you the line of sight magnetic field. If you want to measure the sky plane components, you can use something called the synchrotron intensity, which measures the sky plane component. Of course, often you have to use the assumption that is the magnetic field and the cosmic ray energy density are in equilibrium. So energy densities in magnetic field and this thing in magnetic field and the cosmic ray particles are in equilibrium. You have to assume that, meaning they have reached equipartition. That is what you assume. Atomic hydrogen, I can skip this slide because this I have talked the previous day. These two slides I will rather skip. Now another thing which have though related to H1, but I did not mention that day because too many things would be happening even now when I tell you, unless you work it out in the next slide which will come, you basically don't probably would get it. So what happens is that to interpret large scale structure through H1 observation, what we do, this I did not talk in the H1 thing the previous day, so I will mention a bit about it. One typically assumes that the motions of the gas about the center of the galaxy are circular, and that the angular velocity omega is a decreasing function only of distance r from the center of the system. Now you can ask the question, why should the angular velocity is a decreasing function of distance? The main thing is the galaxy is composed of the meaning, or the interstellar material rather, is gas. This is not a solid body rotation. If you had solid body rotation, then if the angular velocity is constant, then you would have omega r. That means the further away you are, you will be moving very, very fast. Now this is not seen in galaxies, by the way, observationally. If that would have been happening, if you look at the outer part of a galaxy, not our galaxy, which is more complicated to observe, but let's say you are observing a nearby galaxy in H1, and you measure the line of sight velocity, and this could be an H1 galaxy, which makes it easier because all the motions are towards or again or opposite to your line of sight. You measure the velocities, you would find that close to center to certain distance, maybe 1 kilo per sec or so, the velocity keeps on increasing. Beyond that, they say the 100 per sec, in some cases few hundred per sec, beyond that, the velocity roughly remain constant. Okay, so if so, so then V by R, which gives you omega, would obviously be a decreasing function, and it depends on distance r from the center of the galaxy. So this is the assumption which is typically being taken for our own galaxy also, and it follows pretty well because most of these things match up. These assumptions may not be strictly true, but they are valid to first order. The distance from the observer to the emitting hydrogen is, say, let's say r, and she at a distance r naught from the galactic center, and is rotating about it with angular velocity omega naught, that is sun. The radial velocity v is measured positive of the, if the gas is moving away, Doppler shifted velocity, the gas along the line of sight. So this is what is the schematic diagram. You can see how it is done. So the position of the sun is near the top, galactic center is at the bottom, and you are talking of in general of the clumpy gas which is at an angle theta at a distance r, and it's obviously, if the omega is the meaning the omega r is basically the velocity, then you work out what is omega r or the v of that component. So the v is the component of omega r along the line of sight minus the solar velocity, because this is assuming earth velocity is close to the velocity of sun. You should take a difference between the two, that is our own velocity, you subtract from the velocity of that object. So you expand it, this is nothing but trigonometry. You do this omega r cos 90 minus L minus theta minus our velocity omega naught r naught cos 19 minus L. So you can just work it out, and there is no step involved, there is no essentially step jump. So then you get this out. So in red, that's why I wrote down on my own that these two parts, omega r sin L cos L minus r naught r cos L omega sin L, both of these cancel. So you're basically left over by the r naught times omega r, the sin L minus omega naught sin L. So that is what you are left with. So it is basically the angular velocity difference of the sun and the object times the sin L. L is the galactic longitude of that direction L, which is with respect to us or sun. So this slide is taken from Varshaur and Kellerman's radio astronomy, the galactic extracted radio astronomy by Varshaur and Kellerman. So this is what it tells you, meaning it tells you that how to do that. Now, why I mention it, that this was used often to find object at different L, to find their distance using H1 in our galaxy. This relationship is often used, but of course you have to know omega r. With that omega r, if you want to measure distance, you have to know omega r. So initially this was done by observing known clouds at certain distances and velocities. So they were used. So then you can see that the V is equal to omega r minus omega naught r naught sin L is the fundamental equation of 21 centimeter galactic structure analysis. If omega r minus omega naught times r naught is known, r naught is anyway known, omega naught is also known by other measurements. So you can essentially find omega r. Distances along the line of sight in the galactic plane can be attributed to each measured velocity. Now, of course, the practical application of one has several problems. The first I would mention is that accuracy with which the angular velocity rotation curve can be determined. There are other issues which comes up. That's why people go into more details. One will need to go into further details, which in an introductory lecture is not warranted, because we do further in graduate school and so on. So you have to go further. I'm just giving you a basic feeling that okay, what happens for a galactic rotation where omega is a decreasing function of r from the galactic center. And you can indeed, using Doppler shift, can figure out velocities of different clouds. Of course, not along L is equal to 0 or 180 degrees. In fact, this can be done in first quadrant and fourth quadrant only towards the inner galaxy. In the outer galaxy, it becomes difficult because there is no unique solution from this. So now I will go to describe a bit about our own galaxy. Earlier thing was only on interstellar medium. Now let's look at the overall galaxy, how it looks. This is an artist's impression, and what you see is that the central region is the one which looks very luminous. It has a galactic bar. The galactic center is the most luminous thing, and you have the galactic bar, the long bar, and the perpendicular axis of shown. And this is a face-on view. We are sitting in the galaxy, you will never see. But whatever data we have acquired till now, meaning say the 10 years back, this was an artist impression created that way. So the sun is located, you can see from where the coordinate system originates near zero. So that is where the sun is. This is in the Orion arm, and this particular region is known as Orion's path. So the various arms names are written. That is near the central region is the 3 kpc arm. Then you have the Norma arm. Then you have the Sagittarius arm. Then you have the Scutum Centrus arm. Then you have the Perseus arm and the outer arm. So there are, each of these arms have their own name. And you can see that these arms are basically defined by higher stellar densities in those regions. So that is what defines the arms, because you go by what is more luminous, shines more. And that is what using, and remember that this galactic structure analysis you could not do easily using other methods, but these are most, meaning to a large extent, being done through H1. These are also done through other wavelengths using other methods and so on. But remember, this is only an artist impression. We are never 100% sure, because we are sitting inside the galaxy. We have never gone out perpendicular to the galaxy to see this, and you know that's essentially impossible to do that kind of an exercise. So now I will give you the galaxy as the orders of magnitude idea, what are the things and so on. So this, our galaxy is a self-gravitating system. Main observable is a rotating stellar disk. The radius is about 20 kpc or so. The thickness is few hundred parsec. The sun is 8 kpc away from the center and rotates about with a velocity of about 180 to 200 kilometers per second. And revolution period around the solar radius is about 240 million years. To this disk, so which is basically the meaning is added. So this is a disk where the sun lies and so on. There is also a spheroidal component which extends further than the disk. The central bulge is very luminous with radius of the order of 2 kpc. Outer part halo is of lower brightness. So in this previous picture, you see that the central, meaning the bulge region, which is pretty luminous, is shown by this galactic bar, long bar, and this region. So that is the galactic halo, meaning the galactic bulge component. Now the galaxy, let's look at the stellar component first. The stellar system is essentially collisionless, because the typical stellar collision timescale near sun is like 10 to the power 10 times the age of the galaxy. So which is another, the age of the universe is about whatever, billion years or so. So the radiated energy from galaxy is about 4 into 10 to the power 10 times the solar luminosity. So the stars of the galactic disk has small velocities with respect to the bulk rotation velocity. So they are not static. Meaning compared to this, some stars can be more, some can be less. And the total mass of the galaxy, which is dominated, of course, by stars, is about 1.7 into 10 to the power 11 solar mass within a radius of 20 kpc. And the velocities of globular clusters beyond it shows increase in mass. Now you can ask that, why does the mass increase beyond the 20 kpc? I guess you might have already come across things like dark matter and so on. So it is believed that the dark matter, which may be almost like 75% of the overall universe and so on. So the thing is, the majority of the mass comes from dark matter, not the visible matter. So the main thing is that's why that the globular cluster and so on, if you are measuring velocities beyond the solar radius, it still keeps on increasing. The globular cluster, not velocity, sorry, essentially it should have fallen down beyond a point following Kepler's law. It does not. So that is what typically one finds from H1 or other methods, that the velocity remains constant, which indicates that the mass contained is still keep on going up. So the mass to light ratio mg by lg there is around 5 solar mass by L naught within 20 kpc, but this 5 becomes increases to 30 considering total mass of the galaxy. So within the 20 kpc is one thing which is more dominated by meaning I would say visible mass, but as it goes further, where the visible mass further and further goes down, but the total mass keeps on increasing. Yeah, so this essentially gives you the components of the interstellar medium. So here it gives you around the reasonable good estimates of what we know. So the atomic hydrogen H1, the cold part, or the cold H1, has a typical density, as you can see, is roughly about 25 per cc. The temperature is around 100 Kelvin or so. Total mass is around 10 to the power 9 solar mass or so. That is the way. So that is the total mass. Now the one component, the density is much lower, almost 100 times lower, about 0.25 per cc. The temperature is around 8000 Kelvin. And the total mass is very similar, about 10 to the power 9 solar mass. Now the molecular component, the H2, has much higher density, which I have not really gone today. So it has a density which is much higher, about 1000 per cc, which is molecular clouds. And the temperature is less than 100 Kelvin typically. It could be like 30 Kelvin or so in many places. Whereas close to the galactic center, it can reach about 100 Kelvin or so. The total mass is again very similar as in atomic component, about 10 to the power 9 solar mass believed to be. Now the ionized component, on the other hand, has three divisions. One is H2 regions. I mentioned two, but people are making a diffuse component also. So the H2 regions are very clumpy regions which are around the stars, the O or B type of stars, as I mentioned. The density could be anywhere like an Orion nebula close to the center. You can have high densities of the order of 10 to the power 4 particles per cc. The temperature could reach 10,000 Kelvin. And the total mass in such components are 100 times lower, which is like 10 to the power 7 solar mass. Whereas the diffuse, the ionized gas, which is another meaning, which is like H2 region, but it is slightly different because the densities are much lower, and this is more uniformly distributed all across the galaxy, which we typically see through pulsar dispersion, this diffuse component, and its density is pretty low, like 0.03 or so. Close to the galactic center, that is the galactic bulge or so, it can reach 0.3 or so, or even 1. Its temperature is like 8000 Kelvin, very similar, but the total mass, because it's omnipresent almost, it is like the H1, almost like 10 to the power 9 the solar mass or so. The hot component has the lowest density among all the various things which we mentioned. It's like 10 to the power minus 3 or so, a few times 10 to the minus 3. Its temperature is much higher, close to 10 to the power 6 Kelvin or so. The total mass is in the order of meaning lower, about 10 to the power 8 or so. So this is taken from the book on interstellar medium by Lekowitz, Falgaroni, and Reiter. So coming back to our galaxy, that is the P is equal to nkt, that is the pressure. If you just look at, you take out the constant part, which is K. So the NT, that means the particle density times the temperature, goes to about 5 to 20 into 10 to the power 3 Kelvin cm to the power minus 3. This gives you an idea that if N is lower for one component, the T ought to be higher, or vice versa. However, one thing I would like to mention, that this pressure is not necessarily always balanced. The pressure in H2 regions, meaning in all the components, not necessarily balanced all the time. So that means in certain parts like the H2 regions and molecular clouds, they are typically found to be higher than NKT. So that's why H2 regions, they are being not bound by self-gravity or external pressure, so they keep on expanding. On the other hand, molecular clouds are bound by self-gravity and external pressure. So what is the total mass of the galaxy, which is in ISM? It is basically about 5% of stellar mass, which has gone in ISM. The rest 95% lies in other things. So 70% is of the interstellar medium is meaning, or not the interstellar medium, the overall galaxy rather. 70% is mass is in hydrogen, 28% in helium, and about 2% in the heavier elements. So heavier elements means which are typically formed by the supernova explosion. That includes, though carbon, nitrogen, oxygen, you can form by stellar evolution, carbon, nitrogen, oxygen, CNO cycle, and so on. Nitrogen, oxygen, magnesium, silicate, all this can be formed. Above iron is basically where you really need supernova explosion. And these molecules form a continuum of sizes from diatomic to grains, almost like zero point 0.1 micron or so in size, meaning starting from zero point 0.1 micron or so all the way up. So this is what was my talk, rather. So with this, I will rather finish. I would expect that you may have questions and so on. Yeah.
Hello, sir.
Yeah.
So I had a question that you said that the H2 regions, they are not bound by gravity or external pressure, they keep expanding.
Mm-hmm.
So my question is, how much do they expand to? I mean, are they able to expand forever, or do they stop expansion for after some time due to some other reason?
They keep on expanding whichever has been found by measurements, I believe. But whether they stop, meaning, you know that beyond a point when they become very diffuse, it is difficult to say. So I can't say that whether they keep on expanding forever, that is difficult for me right now to say. This I need to check up. I believe whatever to my knowledge, yes, they keep on expanding, but beyond which there is no evidence. One has to see that number. They keep on expanding. Yeah.
Okay, sir. Thank you.
I can see one question in the chat box. What is meant by open cluster? Now, open cluster is more something which is used the term even in amateur astronomy and so on. The main thing is that how the cluster is organized is what is open cluster. That means that sorry, somebody is asking question. Yeah. Okay. That so open cluster is something that where it is not tightly bound. You see stars even at the outer periphery is quite well, and they are not very strongly bound in the center. Meaning, like in globular cluster, they have a very strong density, meaning in number density towards the center, which is not the case in the open cluster. That's what to my knowledge. Okay, it has already been answered also. Hmm.
Sir, I have one question.
Yeah.
Sir, like if there is if the ISM is between say a background source and it is in our observation point, so if we take the absorption spectrum of the background source, so can we probe the kinematics of the ISM? Like
Yes,
it
of
is
course.
done for H1 that you showed, but
Yeah. Certainly,
can
it
it
is
be
done
done by
for
for other
H1.
lens?
Yeah, you can do it. Certainly, people do it similar to H1 for molecular clouds using CO as a proxy, carbon monoxide line, which comes in the gigahertz, meaning the 200, meaning 300 gigahertz or above. So that kind of line comes, rotational vibrational lines. So these things comes, they are in millimeter wave. Quite often, people study interstellar medium using that molecular clouds particularly, and yeah, and some of these can yeah. So you can study other lines. Yes.
Subhashi, just to add to your answer on open clusters,
Mm-hmm.
stellar populations are also different in open clusters compared to globular clusters, where
Yes.
open clusters are usually younger stars, whereas globular clusters are older.
Mm-hmm.
Clusters are also largely confined to the plane of the galaxy, whereas
Mm-hmm.
globular clusters are more uniformly distributed in space.
Yeah.
Any other questions? If not, maybe we can take our usual